Greetings and welcome to this interplanetary edition of Berkeley Conversations. I'm Dan Mogulof from the Campus Office of Communications and Public Affairs. The recent trio of spacecraft arriving at Mars from the United States, China, and the United Arab Emirates has put the so-called red planet back into the headlines. With NASA's Perseverance rover on the move, interest and curiosity are on the rise, and there are questions aplenty. Could life have existed on Mars? How will these missions impact science for generations to come? And how and why did we send a helicopter to another planet? Fortunately, we have with us today an excellent panel of campus experts to answer these questions and many more. Bill Dietrich is a professor of Earth and Planetary Science, and so too is Professor David Schuster. Rob Lillis is the Associate Director of our Space Sciences Lab, and Manar Al-Assad is a graduate student, also in the Earth and Planetary Science Department. As always, we welcome your queries. Just post them on our Facebook Live site where we are streaming this event, and we'll do our best to respond as we go along. But before we get underway, I just want to express our thanks and appreciation to the sponsor of this discussion, UC Berkeley's College of Letters and Science. So folks, I want to go around the room, and Bill, just starting with you, give us a little better sense of what your area of expertise is, how you might be connected to the Perseverance mission, and what's got you excited right now about what you're seeing and learning.
Okay, I'm a geomorphologist, so I'm interested in the form and evolution of landscapes. I also do a lot of work in hydrology, work on river processes, landslides, soil formation, and the connection to ecosystems. I became involved in Mars by an invitation from my colleague, Mike Maven, to join in a collaborative proposal to build the cameras that went on the Curiosity mission. That was back in 2003. That was funded. I joined the group in 2005 and been with it up to the present. And the excitement for me is learning to read the landscape of another planet and have it tell us stories about the evolution of the surface processes and the climate that drove it. And we're seeing lots of really fascinating stuff in our Curiosity site. And I'm looking over the shoulder of David all the time to see the amazing things we're seeing in Desert Crater.
Super, we're going to come back. I have a lot of questions for you, obviously. Rob, let me come to you with the same exact question.
Okay, so thanks, Dan. So I'm the associate director for planetary science at the Space Sciences Lab, and I've been involved in Mars almost my whole career. I'm a co-investigator on the NASA Maven mission. So Maven is an orbiter, was built largely at the Space Science Lab at UC Berkeley that's been orbiting Mars since 2014. It's there to study the processes by which atmosphere escapes from Mars. We know that Mars used to have a much thicker atmosphere in its past, and now it's much thinner. So Maven's been helping to understand those processes and help us understand where the atmosphere went. And in addition, I'm also the UC Berkeley lead for our contribution to the UAE Emirates Mars mission, which just arrived into Mars orbit in February of this year, and it's about to start its Mars mission in about 2 weeks. And I'm really excited to get this new perspective on Mars. I mean, sort of from afar, I'm interested in what's going on with Perseverance and that piece of the climate evolution puzzle, but I'm really looking forward to the new global perspective that the UAE Mars mission is going to give us.
Super. And before I'm going to come to Manar next, but I've just got to follow up on one thing. So I think you sort of mentioned something that not a lot of people are aware of. Are you saying that the I don't know, was it a satellite that's around Mars right now? The Maven project was actually built on the UC Berkeley campus?
5 of the 9 scientific instruments were built at UC Berkeley on the Maven spacecraft. The spacecraft bus itself was a contractor, but more than half of the science payload was built right here at UC Berkeley.
All right, we're going to be asking and finding out more about that as we go on for sure. Manar, give us a sense of what your area of expertise and particular interest is, how you're connected to this or possibly future Mars missions, and what's got you excited.
Thanks, Dan. I am currently a graduate student at the Earth and Planetary Department at EPS. I am studying Earth actually for my PhD. I would like to understand the relationship between the Earth's thermal, magnetic, and evolution and the onset of plate tectonics. And that was mostly motivated by the fact that I've studied other planets and realized that Earth is very special in that sense. Prior to starting this project, I was involved in the OSIRIS-REx mission as a deputy instrument scientist for the laser altimeter. And it is a NASA sample return mission. We acquired the sample successfully, thankfully, in October of last year, and we'll head back to Earth to bring back the sample in 2023.
Samples of what?
Of asteroid Bennu, which is not to scale in the slide that you can see. It is a very old asteroid, a very small asteroid that is in a near Earth environment, and we've not brought back a sample with NASA, a sample from an asteroid before, so this is the first.
Oh, that's really exciting, actually. David, let's finish off this first round with you with that same three-part question.
Yeah, thanks, Dan. I'm a professor in the Department of Earth and Planetary Science, and I'm a geochemist. So most everything that I do is in a laboratory. And so for me to be working on the Mars 2020 mission, where I'm a participating scientist who's specializing in the return sample science piece of the mission, this is something very different for me. This type of work could not be more different from what my normal research is. However, my involvement with this mission ultimately stems from work that I've done on Martian meteorites and also on lunar samples, in addition to most of the work that I do, which is on Earth. And I specialize in geochemistry and geochronology and methods that help us quantify the timing of events that take place at planetary surfaces, including Mars, the Moon, and Earth. And so my role in the mission is to advise on the sample collection. And these are the first samples that we will return from another planet in our solar system. So this is a very exciting, very long-term project that we're doing here.
Super. Look, really look forward to learning more about the sample return. And Bill, let's come back to you. I mean, I'm looking at this really interesting graphic. My understanding is there are 4 separate active missions right now on Mars. Set the stage for us and a little bit of the history. What actually is happening in and around or on and around the planet? And what's the nature of the missions? What should we know about sort of the basics of what's happening at Mars right now?
The basis of the Mars 2020 mission specifically is getting at some really big questions that have to do with when there was liquid water on the planet, when could there have been conditions where life could have existed on the planet. These have been the big motivating questions for the last several rover missions on Mars. And where we are right now in these questions is requiring the sort of measurements that we make back on Earth. And so what's different about this mission as compared to prior rover missions is the sample collection piece of that. If we are looking for evidence of early microbial life that may or may not have existed on the planet, we're at the point now where we really need to make those observations back in the laboratory. Likewise, if we want to know when, if we find evidence for environmental conditions that were amenable to life, or if we find evidence for past life itself in a fossilized form, we're going to then ask, when was that? And that's a very important question because we're interested in comparing what happened on this planet, Mars, to what we understand to have happened on Earth. So those are the big overarching questions of the mission, and these are very big questions on Mars research right now.
Got it. And Bill, let me come to you with the next one. Take us back a little bit. I'm looking at this picture. We've got 4 separate missions. What's the history? How did we get here? And what's still happening from the past?
Well, the history is actually an interesting one, is that there was a well-defined strategy since about 2000. And that was to send orbiters up to map the planet, to understand it as a whole, whether it's on surface features or atmospheric properties. and to identify areas of scientific interest. And then there was a 3-phase plan of landed missions. The first one that I think most people have heard about, which was the MER mission, or the Spirit and Opportunity rovers, the twin rovers that went out. And their goal was to look for any evidence of ancient liquid water. And they found that. Then the Mars Science Laboratory mission, or the Curiosity mission, goal was to find evidence of habitability. And we'll come to that. And we found it. And that then led to the third mission, which is the one that Dave was involved in, the Mars 2020, or the Mars Sample Return mission. So you can see there's a sequence of look at the planet as a whole, make decisions about where to go, see if we find evidence of water, habitability. And now the results of those missions say it's a good plan to go, because we can expect to actually find materials that could get indication or not of the presence of life. And then what we have in addition to that is the evolving understanding of the atmospheric evolution, which the Maven and HOPE programs are about. So there's one thing that's very interesting is that the Curiosity mission is about a year ahead of Maven, and they both have been involved in the question of the evolution of Mars' atmosphere, because clearly Mars' atmosphere has changed tremendously over time. And we're able to compare on-the-ground measurements with atmospheric measurements of changes in the atmospheric composition that tell us the history of the atmosphere. So and then also on the ground, the rovers can do weather detection or monitoring. And for example, Curiosity was there when the big dust storm came and changed the opacity of the sky in a significant way. And we lost one of the rovers. I can't remember, it was Opportunity or Spirit that died during that. And then InSight is a separate idea. It's to look at the interior of the planet. And it's had 500 Mars quakes recorded. It's telling us about, for the first time, the inner structure of the planet. And so you can see sort of an organized effort to tell the story of the planet, to tell its structure and its evolution and the drivers that have given Mars a distinct appearance now, and how different it was 4 billion years ago.
Got it. So help me out here just a little bit, because I'm a little bit confused, and I think some other people who don't follow events on Mars that closely might be as well. The Perseverance rover, that's the latest one, is that part of the Mars 2020 mission, or is Mars 2020 yes, something distinct?
Go ahead, David.
The way that this works is the missions have names. Okay, yeah. And Mars 2020 is the name of the entire mission, and Perseverance is the name of the rover. So that's where some of the confusion may be coming from.
Got it.
So when we say Perseverance and Curiosity, we're referring to the rover itself, but of course those are also very closely tied to the entire mission.
I got it. And so Curiosity's been up there for a while. Bill, what's on its agenda going forward? What are the things that we seek to learn from its future activities?
Well, let me put that in the context of what we've found, because that drives what we look for. Can I do that? And
absolutely.
Would this be a time I can show a few slides?
Please.
Okay. We'll stop other screen. Okay. I'll cancel and wait. You have to get out of the current one. So what I'll show briefly, but while we're waiting for it to come up, oh, here we go, let's see, here's me, here's this. Let's see if you see a screen image. Do you see something now? Do you see an image of arm deployed to John Klein?
Yes. Yes.
Okay. So let me briefly tell you about 6 things that our mission we've discovered since landing here in 2012. Here you see, I think it's important visually to get a sense of where we're sitting. We're sitting in a really big hole in the ground. It's 154 kilometers across. That mountain in front of you there, Mount Sharp, is more than 5 kilometers high. It's higher than the relief of the Sierra Mountains. It's higher than Mount Rainier. The crater is wider than the width of the Sierra Nevadas, or if you like, it's bigger than the distance between Berkeley and Sacramento. We're in a big hole. And we landed here and drove to the spot where you see the arm of the rover. Now, we're right now 300 million kilometers away from Earth, yet we're precisely putting an instrument on the ground to take samples or drill a hole, which is pretty amazing. An earlier look here told us that this was a lake sediment, and I'm going to say something about that shortly. And then there's a selfie of the rover 8 years later, still working, and we used everything on that machine to study these lake sediments. We can determine chemical mineralogy, we can determine the amount of the mineralogy of the sample, we can determine chemical compounds. Specifically, we can determine the presence of carbon and the structure of the carbon compounds themselves, and we can do isotopes, all in situ on this machine. So it's the Mars Science Laboratory, does it there. And what we found is that this lake sediment, which formed in water, has all the elements necessary to life, the essential elements, the carbon, what's called the redox conditions, the conditions where you can accept and lose electrons to gain energy to do your metabolic functions. We found everything in which a microbe could successfully live. And in fact, the water that was associated with this lake was drinkable. So in our first stop, our first drill hole, we found clear evidence of habitable environment. And we also, which was a surprise and greatly debated, we found a fairly significant amount of carbon, and driving 25 kilometers toward that mountain, we found carbon several more times. And so we've also established that ancient carbon that's been there for about 3.5 billion years is preserved and detectable. And that gave us great encouragement of going to Jezero and Perseverance, because we could anticipate if there was ancient life that it would be preserved. Now, let me tell you a story of how we tell stories that get to other things we found. So on the left, we see rounded pebbles coming out of an outcrop of deposits of a river. We can interpret it that way because of the rounding and what we call the sorting. With 100 millimeters, that's another gravelly deposit of a river. On the right, what looks like the edges of a book, the fine layers down to millimeter layering of sediments that would be deposited in a lake. And above that, with lines drawn to help you, is the variable direction of transport recorded in sand. And what this tells us, is a story that tells us that we can describe then that there was a river system advancing into the crater in which there was a lake, in which we were then, we've recorded that at the site, and we found over 300 meters of lake sediment, which then tells us time. The other aspect of interest about life is habitable for how long it exists. Well, our way to get at how long is to ask the duration of an environment. And this was our way to do that. Now, what we find here up in the upper left is that this whole process terminated and then was deposited a large pile of sediment by wind. So aeolian deposits, those are active dunes. As we drove toward the mountain, we drilled holes, and this addresses the title of the conversation. Mars was not always red. We drilled 5 centimeters in the ground, and you can see in most of the instances, the rock is bluish gray.
Yeah.
That's the color of the lake sediments at the time of deposition. And then in many cases, the red of Mars is just a thin dust. But as we drove along here, other things were found. The drilling was done, we could do a chemical analysis and tell by what's preserved on clay minerals of the changing environment in the atmosphere, indicating atmospheric loss that Rob will talk more about. But we also can measure directly methane in the atmosphere as we drove along. We found surprises, relatively low concentration, but pulsative. It increased and decreased, and increased and decreased. And also in oxygen, which is a mystery to us, but of great interest because this is the kind of thing that would be associated with microbial life at depth. So we keep thinking about that and looking for this issue of what controlled that.
So I'm going to stop you for a sec before you go on, because you put a lot of stuff on the table, and not all of us are obviously at the level you're at. So let me get a little bit more basic.
Yes.
So far, we've found no evidence of life on Mars. Is that correct?
No evidence of life on Mars. What we have found are complex organic compounds that could be created by the degradation over time of a compound that could be produced by life, one. And two, we've found the abundance of carbon and the nutrients available for that that's comparable to what would be found in a nutrient-poor environment on Earth. That is, we've found condition in which microbes could survive, and we found compounds that could have been byproducts of life, but we can't at this point claim that it was life derived.
All right. So open question about whether there was life once on Mars.
Yes.
And I have one more, and then I want to move on. I want to get to David.
Sure, sure.
We'll be talking about Perseverance. Do we have any idea what happened to the water and what happened to the atmosphere?
We do, and I think I think that Rob will address this specifically because the Maven mission was directed at that. But there's evidence, and he can explain it. I think he should explain it because Maven was so directed at this. But there's evidence of that the atmosphere has lost a large quantity of its mass to space. But and so there's been loss to from the planet. There's also suggestions that there's been a significant reduction in atmospheric water by reaction with minerals at depth. Is a new idea. So I think I want to defer to Rob because I think he has a fuller perspective on how to describe that.
Okay, we're going to get there. Rob, hang on to that thought. We'll ask you about what the heck happened to the water.
It's an excellent question.
It is a good question. It's the right question. It's just
There's not a clear answer, I would say.
Right,
Yeah.
and I'm proud because I'm a political science major. So who knew?
Well, I'm gonna one up you in a second when I talk about my 5-year-old daughter asking the same question.
Yeah, it's a very important question. Can I turn that around a little bit? The other I want to flip that and say that the strong evidence that there was water on Mars, that there were extended periods of lakes, and that there were rivers and deltas has confounded climate scientists because they can't. This is one of the major challenges on Mars, is to actually explain why there was that condition. It's easier to explain a dry Mars. It's hard to explain a wet Mars when the sun was 30% less luminous. And to explain where was all the conditions, probably high CO2 in the atmosphere, that would favor it. So actually, the geologic and geomorphic evidence calls for a period when there was abundant water on Mars, and it's hard to explain. Climate scientists are struggling to predict why that happened. So it's actually, in some ways, the opposite problem of why was it wet.
Got it. So, Bill, before I move on to David and we start to drill down, if you will, no pun intended, to the Mars 2020 mission and the activities of the Perseverance, what else do we need to know to sort of set the table about Curiosity and what is discovered and how it's led to the current mission, the latest mission? Yeah.
Okay. So let me just change the picture. So so we're looking at a familiar landscape. Let's stop here. And say that familiar in the sense that this looks like Arizona or Utah, but this is Mars. So what the handoff, if you will, from Curiosity, Perseverance is in many forms. Actually, it's in personnel. A significant number of the people who have developed skills and observations in Curiosity are now on the Perseverance team. Secondly, the operations that we've developed, the Curiosity team, in terms of, for example, it takes 50 people to run this rover per day. And it takes a large number of hours to do all the programming. And the Perseverance team has built upon that and has got improved software and procedures to make decisions and program up the rover. And let me remind you that this rover is being driven by people sitting in their bedrooms. They're not a JPL. This is COVID, which is amazing to me.
Wow. So
you just imagine that. So there's literally a guy in his bedroom doing entering the programs to tell the rover what to do. There's a technological building upon, and then I think there's also the persuasive argument that they can expect at Jezero Crater, which is a delta, that if they can find mudstones and they will likely encounter areas with carbon-bearing deposits. That is, the hunt for something that might bear evidence of the past is well motivated by what we've found. It's not just an aside. Before we launched, many of my colleagues said we were not going to find carbon on Mars. It's going to be destroyed by the radiation. It will not be preserved. The chances are terrible. But we found it infrequently. And so I think that suggests that the perseverance effort to look for that has a high probability of at least finding organic compounds. Whether it will indicate life is another issue.
Got it. Okay, David, this is your moment in the sun. Again,
Yeah, so I hopefully, does everyone see the picture on the screen now? Okay, so if our viewers have not watched the video of the entry, descent, and landing, I highly recommend doing so. It's one of the most spectacular things I think that I've ever observed. What you're looking at is the landing of Perseverance rover into Jezero crater on February 18th. I'll tell you why. What Bill just said, all of those reasons led us to Jezero, and I'll explain why we selected as a community this crater. But I just want to say a couple of things. We're only on day. Sol is the word that we use for the Martian day. We're only on Sol 68, right? So we've just begun this journey. And we're literally just starting to orient ourselves and figure out what we're doing. But the big questions that we're trying to address are the ones that Bill already laid out. Was the ancient climate of Mars habitable? Could life have even existed? As Bill mentioned, and he showed you some imagery there, and I'll show you more, there's clear evidence that water flowed at the surface of the planet. But we don't know when that was very well, and we also don't know how long that lasted. And so we're trying to address these questions, and as I've said previously, we're going to try and answer these questions with samples that we're going to bring back from Mars in the form of these little cores that I can talk about in a second. This is where we've landed. This is Jezero crater. Compared to the crater that Bill's in, this one's not as big. This is a smaller crater. And the reason that I'm showing you this photo is this photo has some of this evidence of past water existing on Mars and flowing into this crater. So the star is where we landed. This is where Perseverance rover currently is. What you're looking at in this image, this is the rim of the crater. So this crater makes a giant circle. We're sitting in this hole. And when Bill and I look at this image, we immediately see this feature right here. And I'm highlighting it for everyone, so hopefully you can all see it. This is a delta. We see very similar sorts of features on Earth. I'll show you a picture in a second. This is very clearly indicating that at one point in the past, and again, we don't know exactly when this is, although we have some ideas. I think it was somewhere in the vicinity of about 3.5 billion years ago. Water appeared to have flown into this crater and formed this delta. And this sort of feature forms when a river carries sediment and it flows into a lake. Okay, and so the reason that the scientific community, this was done, some people may not appreciate that this was very much a democratic process by which people made proposals about where best to go, given all of what Curiosity and the previous rovers learned. The idea was, let's figure out where's our best chance to find this evidence of past life in the form of fossilized microbes, potentially. Where's the best opportunity to find some information about when these environmental conditions, specifically the liquid water, existed. And so this is a cartoon depiction of what we're imagining this lake to have looked like. And last night I mentioned my 5-year-old daughter. In preparing this slide, I showed this to my 2 daughters, and just to get approval for the color scheme that I showed. And amazingly, my 5-year-old daughter, I pointed this out, and she said, "Okay, but where did all the water go?" Right? This is a very, very good question. Bill's point on that question is how can we explain the water there in the first place is a more difficult question to actually answer. But the big questions that we have on this mission, specifically in Jezero crater, was when was that water there? When was there a lake? When was this sediment deposited? And importantly, and this is almost as important a question in my mind, is how long were these conditions there? How long were the environmental conditions such that liquid water was stable? And this relates to the third question, which is, could life have existed at that time under those conditions? And I want to show you what an example of such a delta looks like on Earth. This is a photograph from somewhere up in British Columbia, I believe. And what you're looking at is a delta, a beautiful example of a delta here on Earth. You can see the flowing river water and this braided network. And what I want to point out is you can also see, obviously there are trees in the background, but you can also see that there's a lot of greenery and colorful evidence of biological activity in those sediments themselves. And this is the setting where we think we have a good chance of finding evidence of this if it was there at Jezero Crater at whatever point in time in the past that lake existed. And so we put Perseverance on the ground, and this is imagery from Perseverance rover inside Jezero Crater. What I've highlighted for you over here is the delta. So we're looking up at the face of that delta. Obviously, this looks very different from the photograph that I showed with the lake. You see no evidence of vegetation whatsoever. There's obviously no liquid water. And yet we have very good reason to understand that that delta formed at some point in the past by the action of the flowing water. And what we are now tasked with, right now we're orienting ourselves and trying to understand what we're looking at. But my role in this mission is to help with my colleagues on the team to make decisions about which samples of rock should we collect? Where do we go in this image to go pick up one of these sediment cores or bedrock cores and bring them back to Earth to answer these questions? So this process of looking at this image, making informed decisions about where we should go, where we want to go as scientists, where we can go, where we can't access everywhere in this image that you're looking at. This is how this process unfolds, and this is where we are right now.
So David, I'm gonna go over to Rob, and after that to Minar. Before I do, I want a couple of other questions. I believe I read somewhere that this disappearance, or when water existed a long time ago, we're talking about billions of years?
We're talking about almost certainly more than 3 billion years ago. But as I said, we don't know exactly when. So the questions about this fan, and by the way, the way that we know when right now is entirely based on looking at the densities of craters on the surface of the planet in different regions. Very simply put, the longer the amount of time a surface was sitting there, the higher the density of craters. And these are impactors that have constantly been bombarding Mars. They also hit Earth, by the way, and the moon. You can look at the moon, is also covered in craters. So that gives us some idea about when, but it's a rather crude quantification of when. That method of telling us when Jezero Crater existed and when this delta existed pushed things into about 3.5 billion years ago. And this is of interest because this is in the vicinity of when we understand the earliest forms of life are preserved, 3.7 billion years and a bit older on Earth. And so part of the main reason for going to Mars is this is, as Bill pointed out, there are places on Earth that look very much like the photograph that you're looking at right now. This is a very familiar looking planet. And there is reason, because of all of this evidence of liquid water, there's reasons to ask the question, perhaps life could have emerged and existed under those conditions in the past on Mars, much like it did on Earth. This is a huge outstanding question in science that remains. We do not understand where life came from and the origins of life. This is it can't be overemphasized that is a huge outstanding question.
And I should add that the time he's talking about is the same age as what we're finding in Gale Crater. That is, we're talking around 3.6 of the lake sediments, 3.6 billion years, for the lake sediments that I described. So we're looking at might be similar timed events, which would be sensible because they're recording perhaps something that was global and a global climate event.
And that's a really important question that we're trying to get at. Was this a global event, or was there just, for some reason that we don't fully understand, a catastrophic outpouring of water into Jezero Crater? Everything we looked at happened over some relatively short amount of time. Locally, it dried up, and here we are. That's possible, right? So the global versus local question here is important.
Got it. So Rob, let me come to you. Talk to us a little bit about the Maven mission, how this all fits in with the search for answers to some of these really profound questions that we've been hearing about so far.
Sure, no problem. Just go to full screen. Okay, so briefly before just jump into that, this is a map of where the two craters are with respect to each other, the two rovers and the InSight lander, so that viewers have an idea of that they're actually not that far from each other on the planet. But sure, let's move to the Maven mission now. So the Maven mission has been orbiting Mars since 2013, and the idea is to understand the processes which drive atmosphere to escape from Mars. We know, given all the geomorphologic evidence, there's geochemical evidence that Mars was absolutely much wetter in its early history, at least episodically, and that requires a much thicker atmosphere. If you were to pour a glass of water out of Mars today, it would just boil away immediately. Not because it's hot, it's not hot, but it's such low pressure. There's just a very thin atmosphere there. But Mars used to have a much thicker atmosphere, at least 30 to 100 times thicker than it is today. So the question is, where did all that atmosphere go? And some of it could have gone into the crust. There's definitely some evidence of so-called carbonate minerals forming in the crust. So some of that atmospheric CO2 could have gone into the crust, but there's not really enough of it that we've found so far to explain the disappearance of the atmosphere. So if it doesn't go down, it's got to go up. And so, so Maven was sent to understand the processes that drive atmosphere away. In particular, the interaction of the Mars upper atmosphere with both the solar wind and the solar extreme ultraviolet flux from the sun. So as the animation shows here, the orbit of Maven shows it getting close enough to actually dip into the atmosphere on every single orbit, but also get far enough away to get a global view of the atmospheric escape. And as mentioned earlier, Maven has a significant Berkeley component. I said 5 of the 9 instruments were built at the UC Berkeley Space Sciences Lab, and they are shown here. Just going through them briefly, that superthermal and thermal ion composition instrument there actually measures the ionosphere of Mars, the different composition, things like oxygen, carbon monoxide, carbon dioxide, nitrogen as well, and also measuring those ions not just close to the planet, but also far away as they're being stripped off from the planet by the solar wind. And then the solar energetic particle detector is there to see the effects, to characterize the high energy particle radiation that comes from the sun that can also drive atmospheric escape. The solar wind ion analyzer is just to measure the solar wind itself and to have an idea what it's doing. The Langmuir probe also measures the ionosphere, the density of electrons, and the solar wind electron analyzer measures what's called magnetic topology, or the magnetic field lines that guide the atmosphere as it leaves Mars. And then shown here on the lower right is a simulation of the patterns of ion escape from Mars. And those are enhanced whenever there's a solar storm, a so-called coronal mass ejection, when the sun ejects, belches out billions of tons of hot plasma. That's what causes the aurora on Earth. Mars, without a protective magnetic field around it, all that high speed, high energy solar wind plasma impacts the atmosphere directly, and rates of atmospheric escape can increase by up to a factor of 100 during one of these solar storms. And the interesting thing is, we're pretty sure that in the early solar system history, the same kind of time that Bill and David were talking about, 3.5, 4 billion years ago, the sun was, while it was much dimmer in the visible and in infrared, so Mars would have been receiving less overall radiation, the ultraviolet radiation, the high energy radiation, there was actually about 4 to 6 times more of it back then. And also the solar wind was also much stronger. So these storms and the effects of these solar storms on atmospheric escape at Mars that Maven has been investigating were much more common in the early solar system. So in understanding the processes today, we can extrapolate backwards in time to estimate how much total atmosphere might have been lost. So that's sort of an overview of the Maven mission. Dan, I can go on to talk about the UAE mission, or if you have a few more questions about Maven, happy to answer them.
Actually, I'm going to do neither, if you don't mind. I'm going to use my moderator's prerogative. And actually, before I go to David and Menard to talk about sample return, I want to bring into the mix here some really good questions we're getting from folks who are tuning in. So here's the first one, and it's a jump ball. I'm not sure which of you are best positioned to answer. Here's the first one. Why are so many geological features on Mars so massive compared to Earth? For a planet a quarter the size of Earth, geological features like Olympus Mons and Valles Marineris would surpass nearly all mountains and canyons that we have here. What's up with Mars that allows for that? Anybody?
Much lower gravity is a major part of that. So the mountains can just get that much taller without gravity pulling them down. I think that accounts for a lot of it. The gravity is about 1/3 what it is on Earth, and the topography is 3 to 4 times larger than it is on Earth. I mean, Bill, you're the geophysicist. What do you think?
Okay. Well, one thing that may surprise you is it's argued by many that on Earth, the heights of mountains are limited by erosion. And in fact, some have argued that mountains get high enough that they elevate to the point where they capture ice, form glaciers, and the glaciers buzzsaw them off. Others have argued that simply gravity comes into play and the mountains get high enough, they gravitationally spread. So there's a self-limiting process associated with gravity and erosion that limits the size of features on our planet. So that's a contributor. I don't know whether others, maybe David, you can comment whether the Tharsis is associated with some kind of exceptional superplume.
Well, what I was going to add to that is the apparent lack of plate tectonics, right?
Yeah.
So there's not the erasure mechanism that we have here on Earth, where such large scale features, even if they were produced in the past, would have been erased through time by the means that Bill mentioned, through erosion, but also plate tectonics. And this is also one of the reasons that, unlike on Earth, we have rocks that are very old that are exposed at the surface. And this is indeed one of the main reasons for collecting these samples from Mars. So all of these reasons are part of the answer. That's a very good question.
All right, so you broached sample return. Let's jump into it. David, talk to us a little bit about why sample return is so significant and so important.
Yeah, so as I said previously, where these questions are right now require measurements to be made back on Earth that simply cannot be made in situ with a rover. So if we're looking for evidence, fossilized evidence of microbes, we can't observe these things from a rover directly. And so one of the main reasons, there are two main reasons for bringing samples back to Earth. One is to look for this very fine scale imagery that we can only conduct on samples in a lab, mineralogical analyses of them, chemical analyses, isotopic analyses, and looking for that evidence of past life in a fossilized form. But then also the geochronology piece of this. What my laboratory looks like at Berkeley Geochronology Center, it's approximately the size of a small house, right? We can't fly such equipment to Mars. It's just not feasible to do so. And so where we are right now is we need to bring the samples back. And I have a slide here to show you. If you look at left, hopefully all the viewers can see this slide that we're looking at. This is one of the samples this is an example test sample using the hardware, the drilling hardware on Perseverance. And each one of these rock samples is about the size of a piece of chalkboard chalk that we'd use in a classroom. They are very small. The samples in comparison that we returned, the only other planetary body that we have thus far returned samples from is the Moon. And those samples, roughly 1,000 pounds of rock from the Moon came back to Earth, okay? In this mission, we're gonna return at most 28 of these little chalk-sized pieces of sample. This is a very, very small amount of mass. And the way that this works is the rover has a drilling mechanism that is all obviously robotic. And this simulation that you're looking at shows how this works. The drill comes down onto direct contact with a rock, and it drills into the rock. And that core that is within that tube that drills into the rock goes directly into, you're going to see it's transferred into a contained vessel. And that was what was shown in the previous image. And that vessel is then containing the sample, which will be picked up in a subsequent mission and returned to Earth. At the end of our mission, at least after we collect all of the samples and plan to return these 28 little pieces of chalk-sized rock and soil to Earth, we are literally going to leave them on the ground on Mars, at which point a subsequent mission will fly to Mars and pick it up off of the ground and load that onto a rocket. And that rocket will then be launched off of Mars, out of the Mars gravitational potential. And that will then go onto a spacecraft that will return to Earth. As you can see in these three images here, this mission, the Mars Sample Return Mission, I apologize, is now in the design and development stage. So over the course of the next 3 to 6+ years, we're going to be operating Perseverance, driving around, identifying these samples, collecting them, if all goes well. This center image here for the Mars Sample Return is not going to launch until 2026 at earliest. We will not get these samples back on Earth to make the sort of measurements that I make until 2031 at earliest. And so when I say this is a marathon, and we're already many years into all of this, this is a serious marathon and a very complex undertaking that we're talking about getting these samples back.
Yeah. So Manar, the process David just described, we're talking, I'm sure, billions and billions of dollars, 10 years. What makes it worth it? What kind of added knowledge do scientists like you hope and believe these samples may bring to humankind?
It's a great question. And one of the precursors to that question is that we do already have extraterrestrial material on Earth from space that came here naturally. We have thousands and thousands of meteorites that fall onto Earth every year that we collect and give us great knowledge about space. Some of them come from asteroids, some of them from comets. We have lunar meteorites, and we even have Martian, about 270 Martian meteorites. And those have greatly extended our knowledge of the history of the universe, of the solar system, and of the planets. However, the problem with meteorites is that as they're falling through Earth's atmosphere, they go through chemical and thermal changes due to the heating from friction with the atmosphere that considerably changes their properties. And so we don't really know what they were like before they came to Earth. And that limits our understanding of them. For example, if something contained liquid water or ice, that will likely evaporate on its way to Earth. And we will have no knowledge of the state prior to Earth entry. The other thing which is important is context. We don't really know exactly where they came from, which body, and even on Mars, we don't know where on Mars. And you've seen that it has very different geological features. It has craters and deltas and volcanoes. And so in order for us to understand what these samples really can tell us, we have to know the context of them. And David mentioned earlier that we don't even know the origin of life on Earth or even if it exists on other planetary bodies. So missions like the OSIRIS-REx mission actually they're motivated by understanding the origin of life and organic material, because believe it or not, Bennu, which is a very small 500-meter radius asteroid, it hasn't really gone through different the chemical changes that large planets have gone through, because it's not as hot, and there's no differentiation in chemical reactions that exist in high temperature and pressure. Therefore, it preserved some of the primordial material that formed our solar system. And the reason we went there to grab samples is we want to know what was the organic life like prior to the formation of planets, and could asteroids have brought those organic material to planets, not only organic material but also water and volatiles, which we consider as a precursor to life. So when we usually get samples, we will get a sample or when we see meteorites, we just see a rock and we have no information about its history.
Hang on one sec. What are we looking at right now? I just saw something pop up on the screen.
Yes, that's what I'm going to talk about. Yeah, so when we get them, we usually get just a rock and we have no idea where it came from. This is Bennu. This is the asteroid that OSIRIS-REx went to. And prior to acquiring the sample, we spent 2 years orbiting this asteroid and studying every bit of it in so much detail to decide where we're going to get the sample. And then once we've decided, we even went in that region, studied it even in greater detail to the point of counting every like 2-centimeter rock in that region in order to understand it very well. And then after that, we performed the maneuver to collect the sample, which you could see here. And this is robotic, unmanned. And the spacecraft approached the asteroid and then grabbed the sample and moved back away from the asteroid. And in May, it will start heading back to Earth to give us the sample.
You know, I have to say, as a layperson, it kind of boggles the mind. You showed the picture of that asteroid, and in a different context, a different size, it looks like a piece of rock that you would not care about at all. It's ugly. It has it seems to have no defining features. And yet you spent 2 years studying this? Yes, we did. One of the reasons, I mean, there is obviously a lot of scientific interest in characterizing this asteroid, but other than giving context to the sample, there are actually very interesting geophysical processes that happen on asteroids that we don't observe on planets. For example, there's a process because of the size of the asteroid, because it's so small. When it absorbs radiation from from the sun, the side that is facing the sun, and then it turns around a little bit and then re-emits that radiation. It gives it a little thrust. So it has this engine that is preferentially always acting in the same direction. So it changes the orbit of these small bodies over long periods of time. And that's why we don't exactly know where they're going to go. And it's important to study these processes to understand the collisional the collisional possibilities with Earth and other planets as well. Got it. Unbelievably, we only have about 5-6 minutes left. This is so fascinating. I want to spend just a few minutes talking, because obviously what we all have in common here is UC Berkeley, and the heart and soul of the university is obviously its research enterprise, but also its educational mission in terms of students. And I'd like each of you to talk a little about either your own experience or current experiences about what kind of opportunities our students have, particularly our undergraduates, to get involved and get hands-on and to really take full advantage of this incredible work that you guys are doing. David, you want to lead that off?
Sure. For undergraduate involvement in specifically the Mars 2020 mission, I'm not so sure. I have a
or just graduate, or even graduate students.
I have a first-year graduate student, Drew Gorin, who's involved, and he's been loving it. I mean, he's been thrown into the deep end. This is a generational sort of an endeavor. This is all, kind of by coincidence that here we are. One aspect of the Mars 2020 mission that really strongly resonates with me is the fact that these samples, as I just showed you, that are going to come back 10 years from now, if all goes well, these are going to be the samples that the next generation of scientists work on. And these are the next generation of scientists. This is the generation that we're training now. You know, Manara is going to be, it's her generation that's really going to be doing the groundbreaking work on these after they come to Earth. I, as I mentioned, have benefited from working on Apollo samples that were collected before I was born, right? And so I very much know the value of having access to these samples. And in my mind, at least what I'm telling me right now, myself right now at the beginning of this marathon, is this is kind of the ultimate form of paying it forward to the next generation of scientists. So student training at the graduate level, absolutely. At the undergraduate level, Bill perhaps can speak to his experience. There are certainly opportunities, the most important of which is asking questions, right? Asking those good questions from a fresh mind. That's incredibly important in this work.
Bill, I think you just got your cue.
Excuse me. So I have two comments. One, I have every single photograph that what's called the mass cam, the two cameras, 34 millimeter, 100 millimeter cameras taken are presented to the public as soon as they're downloaded. So everybody has access to them. But what I can do with undergraduates is put them in context. And so I've had undergraduates as undergraduate projects look at photographs and do geomorphology with it. That is, and try to interpret the landforms and the deposits. But in a more intensive way, I've had two graduate students, one finished a PhD, one currently in it. And they've not just participated, they've led. The one, Marissa Palousas, who's now a professor at Dartmouth, was involved in what's called operations. She'd dial in on a daily basis and help make planning and decisions. And led her to now having an active research program where she's doing both work on Mars and looking for what we call Mars analog on Earth, because actually what the experience in Mars does is it makes you ask questions about Earth you'd never think to ask. For example, take the picture of Davis Delta or Jezero Delta. How much water did that take to make? We have not asked that question on Earth. So now we have students going back to Earth asking new questions from their experience on Mars. Alex Brick, who's currently with me, has spent 18 months having a very major role in deciding what images to take, what path the rover should take for as it traveled onto this erosional future we've been very fascinated by. And so he's had deep participation with a broad team, and it's been an inspiration for looking at other planets, for sorting out the how we can interpret imagery and chemistry to tell geologic and climatic history. So the students that we've had at Berkeley are not just getting some data; they're active participants in the mission role itself. And I want to emphasize that the mission really welcomes that. They welcome student participation. They welcome them having a significant role. They put great emphasis on this.
Yeah, and Rob, my understanding is you yourself were a Berkeley graduate student, and that was your point of entry into all this?
Yeah, that's right. There was I was working on yet another instrument that was built by Berkeley that went to Mars on the Mars Global Surveyor mission back in 1997. I was still in high school back then, and I came to Berkeley as a grad student. And one thing that's eternally true, and this speaks to there's always a lot of interesting work for undergrads and also grad students to do, is that there's far more data than there are people to analyze it when it comes to Mars Global Surveyor, and Maven, et cetera. And so we always welcome undergrads coming in. And I was lucky enough to basically have an almost untouched data set from Mars Global Surveyor upon which to do my PhD. And there were some great discoveries that came out of that. And it was just because we just need smart, interested people to look at the data. And I myself have had 4 undergrads over the years. We have a couple of grad students now, and we always welcome people because there's so much to discover in these data sets, and they will continue to be the source of many scientific papers, many theses for years and years to come.
Yeah, Manar, let me finish with you. I mean, you are a graduate student. What's it like to sort of be in the hotspot at the center of the action, and what's it meant to you?
It meant a great deal. I started my research in space as an undergraduate student, and like all of the professors here have mentioned, it started with being curious about space and then asking a professor if they need help with it. And 10 years later, I am still working on planetary missions, and I have had the opportunity to even be a deputy instrument scientist on one of them. And it definitely drove me towards staying in this field and working more on it. And it's definitely going to be a part of my PhD here in Berkeley, is to study the data that we got from OSIRIS-REx.
Thank you. So sadly, really, truly sadly, we're at 6 o'clock. Absolutely fascinating. We've got a lot of questions we didn't get to, so we might want to consider doing another of these as the Mars missions proceed. Before we end, I want to give special thanks to Michael Menga, the chair of the Earth and Planetary Sciences Department, as well as Francis Hellman, the Dean of Mathematical and Physical Sciences. And with that, Bill, David, Manar, and Rob, thank you so much for your work, for your expertise, for your time and your enthusiasm. And to all of you, thanks for joining us. Have a good evening.
Thank you.
Thank you.
Thanks.